Welcome to the deep dive. If you've been following artificial intelligence at all, you know we are just swimming in complexity.
Especially with multimodal AI.
Exactly. The really sophisticated stuff, the systems that have to deal with text, images, audio, video, all at the same time.
Right, and if you're trying to build one of these, it's not a clear path.
It's a sprawling wilderness. Choosing the right algorithm, it feels less like engineering and more like, I don't know, guesswork.
Educated guesswork, maybe?
Okay, let's unpack that. Our mission today is to see if there's a map to that wilderness. Is there some kind of, universal rule that connects the hundreds of AI algorithms out there?
And we're diving into some really fascinating research from a team of physicists at Emory University.
Right, who think they've found one. They suggest that not only does a principle exist, but it can actually organize the entire field.
And that's critical because real-world problems are multimodal. They're messy.
A self-driving car, for example.
Perfect. It's juggling what it sees, LiDAR signals, GPS data, all at once. Or a medical AI looking at scans, patient notes, genetics.
So for the developers, this is what they call the design space explosion.
It is. Every time a new task comes up, it feels like they're starting from scratch, inventing a new mathematical rule, a new loss function, just for that one problem.
And these physicists, the Emory team, they just stopped and asked a really basic question.
A very fundamental one. Does every single problem really need a brand new solution? Or is there a simpler way?
And their answer is just. It's so interesting. They came up with this metaphor of a periodic table for AI.
Right, but before we get into the table itself, we have to understand the idea behind it.
The master principle. What is the one thing they found that connects all these different successful AI models?
It's a concept from information theory, and it's actually beautiful in its simplicity. It's compression.
Compression. So just making things smaller.
In a way, yes. Every successful model is essentially doing the same thing. It's compressing all these different kinds of data, but only just enough.
Just enough for what?
Just enough to keep the pieces that actually predict the outcome you want while aggressively throwing out all the noise and all the redundancy.
Okay, so define noise in this context.
Yeah.
Like, what is redundant information to a self-driving car?
Okay, so if the car's camera sees the same parked car for 10 seconds straight while it's waiting at a light, that's redundant information.
You don't need all 10 seconds of that data.
Exactly. Or if a medical AI is analyzing a patient's breathing, the sound of the air conditioner in the background, that's noise. The model has to learn to mathematically identify that and just get rid of it.
That makes perfect sense. So let's go back to the periodic table idea. Is that just a nice way to talk about it, or does it actually function like a classification system?
It's much more than an analogy. It really is about classification. Just like elements on the real table are grouped by their properties.
Their electrons and so on.
Right. Well, AI methods can be grouped in these cells based on the specific trade-off they make, how much information they keep versus how much they compress away.
But I have to be a little skeptical here. The real periodic table was predictive, right? It showed chemists where to look for elements that hadn't even been discovered yet.
That's the perfect question.
So does this AI framework just organize what we already have, or can it actually point us to new, maybe even better algorithms?
It is absolutely predictive. The underlying math, which we can get into, allows for that. If you know the exact information trade-off you need for a new problem, the table can tell you where the best solution should be.
Even if no one's really built that solution yet.
Right. It moves you from what you called guesswork, what we call AI experimentation by instinct.
Just trying things until something works.
Exactly. It moves you to AI design by principle. You start with the goal, define the trade-offs, and the framework shows you the right mathematical path.
Okay, that's a huge shift.
Yeah.
So to understand how that works, we need to look under the hood, at the engine room of AI.
Which means we have to talk about the loss function.
The loss function. So for everyone listening, that's basically the mathematical rule an AI uses to figure out how wrong its answers are. It's the guide that helps it learn and get better.
Correct. It's the internal compass.
So why is that compass causing such a huge problem right now?
Because every time a developer combines new data types, they tend to build a very specific, a bespoke loss function just for that task.
They're only thinking about that one problem.
They're just focused on getting the best accuracy score for that moment. They're not thinking about any kind of universal principle. And that's where this team solution comes in.
The VMIBF.
The variational multivariate information bottleneck framework.
Right. The mouthful. How does that change the game for designing these loss functions?
The VMIBF is the architecture that makes that compression principle we talked about actually work. It's the bridge. It connects the math of the loss function directly to that decision of what information to keep and what to ignore.
So it's not a specific function, it's a framework for building them.
You can think of it like a control knob, a really precise, calibrated one. Instead of writing a whole new program, you can just dial in your needs.
A control knob. I like that. Give me an example. How would two different developers use that knob?
Okay, let's take two scenarios. First, a radiology AI. It's looking at an MRI scan and a doctor's written notes.
Okay.
You need maximum detail from that MRI image, right? But the notes might just confirm the patient's age. So you turn the VMIBF knob to preserve almost all the information from the image, but you can compress the text channel really aggressively.
Got it. What's the second scenario?
An autonomous tractor. It's analyzing soil chemistry, weather data, and images of the crops. The soil data is critical, but it doesn't change very fast.
But the weather data is changing constantly.
And it's full of redundancy, so you dial the VMIBF to retain that crucial soil info, but you let the model be really selective about the weather inputs. The framework enforces the right information flow for that specific job.
That really clarifies it. And it highlights the difference in approach here. The machine learning world is so often focused on one thing: accuracy.
Right. Whatever it takes to get the score up.
But these were physicists. They weren't just happy that something worked. They wanted to know why it worked. They were looking for the fundamental principles.
Exactly. It's a completely different mindset. They spent years just writing on whiteboards, trying to boil all this complexity down to its mathematical core.
Which led to this amazing story about the lead author, Essam Abdelhalim.
It's fantastic.
After he finally solved the foundational math, he was leaving campus, just completely buzzing. And he checks his Samsung smartwatch.
And what did it say?
The watch had picked up on his racing heart rate, his, physiological state, and it concluded that he had been cycling for 3 hours.
That says everything, doesn't it? That wasn't just solving a problem. That was finding a deep, unifying connection. That's the physics perspective. It's a search for elegance.
It really is.
Yeah.
But for most of us, for businesses, the real question is about utility. How does a breakthrough like that actually make a difference on the ground?
And that's where it really proves its worth. After they built the framework, they tested it against dozens of existing AI methods on benchmark datasets. It held up.
And what are the practical benefits for a developer?
Well, first, it's just easier to create the right loss function. That saves a ton of engineering time. Second, and this is huge, the models can often solve problems with much less training data.
Let's pause on that, because that has massive implications for sustainability.
It really does.
I mean, we hear about these huge AI models costing millions of dollars to train with a giant carbon footprint. So if you can guide the model to only use the essential data,
You need less data to train it, which means less computational power, less cost, less environmental impact. Smarter with less becomes a core strategy.
absolutely. So what's the third benefit?
Prediction. The framework helps you predict which types of algorithms will work best for a new problem. And just as important, it helps you see where they're likely to fail.
Because the loss function is really the model's incentive system.
That's a great way to put it.
If you're rewarding it for the wrong thing, if you're telling it to keep junk data, it learns bad habits.
Yeah.
And that's where the real danger is, isn't it?
It is. That's how you get subtle bias or models that just fall apart when they see something unexpected. The model is just doing exactly what it was mathematically told to do.
So for the person listening to this, the person who has to trust or buy these systems, this all comes down to trust and auditability.
Exactly. If you can explain in plain English what your model is being trained to keep and what it's trained to ignore, that builds transparency.
Which leads to the key takeaway for business leaders. The action isn't to go become an information theorist.
No, not at all. The action is to start asking better questions.
Better questions of your AI teams, of your vendors.
For too long, we've had this cargo cult AI problem.
Explain that.
It's where companies just copy what the big players are doing, using some massive model or a complex loss function without understanding why. They just do it because Google did it.
And when you do that, you inherit all of its problems, its biases, its inefficiencies.
You get a black box that was designed for someone else's problem.
So the framework gives you the language to push back. What are the specific questions they should be asking?
You need to shift the conversation. It shouldn't just be how accurate is it. It needs to be what is the system mathematically optimizing for?
And what trade-offs are being made between compressing the data and getting an accurate prediction?
Precisely. And how do those trade-offs align with our actual business goals? If your vendor can't answer that, you are buying a black box.
That's a fundamental shift.
Yeah.
And the researchers aren't stopping here, are they? They're already building on this work.
They're moving into a really fascinating new area, using the framework to try and understand patterns in biology.
Specifically cognitive function, right? The human brain. That sounds like a huge leap.
It is. But they're looking for similarities in how we compress information. Our brains are constantly taking in massive amounts of sensory data and compressing it down to what's essential.
So they want to see if the brain's methods look anything like the mathematically optimal methods from the VMIBF.
Exactly. It's about using the artificial system as a lens to better understand the biological one, and vice versa.
It's an incredible ambition, and it gets to the heart of the issue, really. AI got powerful much faster than it got understandable.
It did.
And this framework, it signals a healthier direction. Less mystique, more engineering discipline.
That's the goal. This shows that we don't have to accept chaos as the price of innovation. We can have structure. The end goal isn't just an accurate AI, it's one that's explainable, reliable, and trustworthy when it's out in the real world.
And that leaves us with a final, provocative thought for you to take away. If a single mathematical framework can bring order to the chaos of hundreds of AI algorithms, what other massive chaotic systems in our world might also boil down to a simple underlying principle?
Things like financial markets or complex ecosystems.
Exactly. What if we could find the right mathematical lens to see the simple, predictive rule hiding underneath all that complexity?
It's a powerful idea.
Think about that the next time you face a problem that feels just overwhelmingly complex. Maybe what it needs is a new way to think about compression. Thanks for joining us for this deep dive. We'll see you next time.